Hello, my name is Andreas Bluhm. I'm a postdoc with QMath at the University of Copenhagen, and this is my talk for QPL 2021. And I want to talk about maximal violations of steering inequalities and the matrix cube, and this is recent joint work with Nechita. So as you've already seen, the main topic of this talk is the maximal violation of steering inequalities. And the question you asked there is, for an arbitrary steering inequality, how much smaller is its LHS value than its quantum value? LHS stands for local hidden state model, and it's a bit like the local hidden variable models for violations of Bell inequalities. And the main tool that we use in this talk is the connection to free spectrahedra, which we establish. And in particular, we use the matrix cube, which we will meet later. So let me start with quantum steering. Quantum steering has a nice operational interpretation given by Weisman et al. In 2007. And it comes with this picture here. So there are two parties, Alice and Bob doesn't trust Alice. But Alice wants to convince Bob that she has prepared an entangled state row. And she can perform measurements indexed by X. And she can announce the outcomes A to Bob. So there are G measurements on Alice's side. They have KX outcomes each. And the quantum systems of Alice and of Bob each have dimension D. And what Alice actually prepares is some assemblage. So an assemblage is a tuple of positive semi-definite matrices, sigma A given X. And they have the property that if you fix X, the measurement, and you sum over all the measurement outcomes, you obtain some average state, sigma bar. And it's the same average state for all X. So Alice can perform these assemblages, and she can announce in advance to Bob which assemblage she will prepare. And then Bob can request from Alice that she performs a certain measurement X. She tells him what measurement outcome A she got. And then Bob in principle can check if he has this subnormalized states sigma A given X at his side, and he can check the frequencies or the trace of these things. And then the question is, when is Bob convinced? Well, he's convinced if the assemblage that Alice prepares doesn't have a local hidden state model. A local hidden state model means that all the sigma A given X are of this form here. So where Q lambda is a probability distribution and the PA given X and lambda are conditional probabilities and the sigma lambdas are states. So this means that if the assemblage is of this form, of this LHS form, what Alice could have done is, instead of preparing an entangled state row, she could have just prepared single system state sigma lambda, according to some probability distribution, sigma lambda, and then announced the outcomes A depending on X and lambda. So in this case, she's cheating. And since Bob doesn't trust Alice, he's not convinced in this case. But if the assemblage doesn't allow for a local hidden state model, he has to accept that that row is an entangled state, even if he doesn't trust Alice. So in this sense, quantum steering is a semi-device independent proof of entanglement. So how does Bob know whether the assemblage admits an LHS model or not? This is where the steering inequalities come into play. So steering inequality is just a tuple of self-adjoint matrices F, also indexed by A and X, and we can compute different values of them. So you always take the trace of sigma A given X and F A given X, and then you take the sum over all A's and X's. And then depending on which value you want, for example, you take the supremum over all assemblages, which allow for an LHS model. And then you obtain the LHS value, which we call VLF. And you can do the same thing, but this time taking the supremum over all assemblages, and then you obtain the quantum value. And if you measure something with a steering inequality which is larger than this VLF, so larger than the LHS value, then you can be convinced that the assemblage that you have does not allow for an LHS value. So that's the idea here. Mostly we will work in the setting where all the measurements that Alice performs have two outcomes. So in the dichotomic setting, where all the k-x's for all x's are just 2. And in this case, we call the steering inequality F unbiased if F plus of X is equal to minus F minus given X for all X in G. So this means that we have just indexed the outcomes as plus and minus. So this is an easier setting. And let's now come to the steering constants, because these are the things we're actually interested in. So the set of steering constants are defined in the following way. So sigma of G and D. So now you fixed the number of measurements on analysis side G and the dimension D. So this is a set of vectors S of length G with entries between 0 and 1, such that if you take any dichotomic steering inequality, if the LHS value is smaller or equal than 1, and you add noise according to this vector S, then the quantum value of the noisy steering inequality should also be at most 1. And the noisy steering inequality Fs is the convex combination of the original steering inequality with some trivial 1 F0. This is particularly easy to interpret if we are in the unbiased setting. So if we restrict to unbiased steering inequality, because then the F0 is just 0. And this means that we just scale the steering inequality by this amount S. So we can scale different elements in different ways. That's why we multiply these element-wise by a vector. And this set of steering constants quantifies how much steerability is available for fixed G and fixed dimension, because it means that you study how much noise you have to add to any steering inequality for fixed G and D, such that its quantum value is also at most 1 if the LHS value is at most 1. You can also quantify this in a single number instead of vectors. So the single number is called the largest quantum violation, and it's just the quotient of the quantum value over the LHS value, and then take the supremum over all F for fixed G and D. So that's can also be interpreted as how much steerability is available for fixed G and D, because it quantifies how large this violation can be if you have fixed the dimension and the number of measurements. And if we restrict to unbiased steering inequalities, we'll just add 0 to the sigma and to the G. So that was quantum steering. And now let me talk about free spectrahedra before connecting the two. So free spectrahedra are studied in optimization theory and in algebraic convexity. And they're given in the following way. So you fix a tuple of length G plus 1 of D by D matrices, which are self-adjoint. And this tuple is called A. So then the free spectrahedron at level n is given in this way. So it's the set of all tuples of length G of n by n self-adjoint matrices, and which fulfill this linear matrix inequality given by the AIs and this A0 here. And then the free spectrahedron proper is just the disjoint union over all n of these levels. So in a sense, this just means you look at all the matrix tuples X, which fulfill this linear matrix inequality here, no matter what their size is. And if A0 is the identity, that's a special case, and we call this free spectrahedron monic. That's the most important case, actually. And to distinguish it, we just write dA instead of this dA hat here, if it's monic. So let's give some examples. One is the already mentioned matrix cube, which has been studied, for example, in this work by Bental and Nemirovsky in 2002. And it's given as X tuples of length G, self-adjoint matrices, size n, which have to fulfill that Xi has operator norm at most 1 for all I. So if you look at level 1, for example, this is actually like a cube. That's hence the name. And it can be written in the form we've seen before as a dA. If you put the AIs as EI and minus EI, where these are the standard basis vectors, and you interpret this thing as a diagonal matrix. And the A0 is the identity, so it's a monic free spectrahedron. Another example is the so-called matrix diamond, which, for example, has been studied in this work by Davidson et al. In 2017. And there its levels are defined as the tuples X, which if you put signs in front of the Xi's, so epsilon I is +1 or -1, and you look at all the different combinations, they have to be small equal than IN. So it's also a monic free spectrahedron, and has been used by Ion Nechita and me to study the compatibility of measurements in this work down here. And this work was also the motivation to study quantum steering now instead of the compatibility of measurements. And in this, what you want to know about this free spectrahedra is you want to know about their inclusion constants. So first, what does inclusion of free spectrahedra actually mean? It means that if you have two indexed by A and B, the dA is included in dB if and only if this is true level-wise. So you look at all the levels separately, and you want that dA at level n is in dB at level n. And then the inclusion constant set is, again, vectors S of length G with entries between 0 and 1, such that if dA is in dB at level 1, then if you shrink dA by this amount S, then it also fits in dB at all levels. And this has to be true for all tuples B of length G of D by D matrices, which are self-adjoint. So this is like the monic version of things. And here, this S dot D just means that I take all the x's in D and you multiply x1 by s1 and until xg by sg. And the non-monic version, I mean, here we fixed the dA to be monic itself, is just replacing the dB on the right-hand side here by some tuple of length g plus 1, and you look at the non-monic free spectrahedra. This you can also do. And as a shorthand, if we talk about the matrix cube, which we'll be mostly doing in this talk, we just write delta square and delta hat square, just for ease of notation. So let us now connect the two things, quantum steering and free spectrahedra. And let's see what they can tell us about the maximal violation of steering inequalities. So first finding is that to any steering inequality Fa, given x, we can associate some free spectrahedron df tilde, where f tilde is, are some matrices depending on this f. I will not go into details here. And then our first main finding is the following. So for an arbitrary steering inequality f, we have the following. So that if the matrix cube at level 1 is constrained in this df tilde, this is if and only if the LHS value of f is at most 1. And in the same way, if the full free matrix cube is contained in the free spectrahedron given by f tilde, this is if and only if the quantum value of f is at most 1. So now we have connected a question about quantum steering to a question about inclusion of free spectrahedra as promised. And now we want to use this to study these violations. So this is why we have to talk about inclusion constants again. And the main finding we find there is that for all G and D, we find that the set of steering constants is the same as the set of unbiased steering constants, and it's the same as the inclusion set of the matrix cube, and the same as the non-monic inclusion set of inclusion constants of the matrix cube. Which makes it a bit easier is if you look at the diagonal case. So for any s between 0 and 1, where you just look at s times the all ones vector, so there all the si's are the same. This is in the unbiased steering constants if and only if for all unbiased steering inequalities f, it holds that if you look at this quotient of the quantum value over the LHS value, if this is so the s is inside the steering constants if and only if this ratio is always smaller or equal than 1 over s. And we define, I mean, if the LHS value is 0 and the quantum value is also 0, we just define this thing to be 1. So in particular, the largest s which fulfills that is equal to the largest unbiased quantum violation, this gamma 0 here. Right. So this is one version of interpreting the set of inclusion constants of the matrix cube. So let's look at another one. And this we can do in terms of set inclusions. So now this L sigma bar and the Q sigma bar are again the set of assemblages with LHS model and just the set of all assemblages, but now you fix the average state to be sigma bar. And of course, the L sigma bar is contained in the Q sigma bar, but we want to know like how much larger is the Q compared to the L. And then we have for all invertible average density matrices sigma bar, that if you look at the set of vectors S of length G with entries between 0 and 1, that if you shrink Q by S and you add some trivial assemblage depending on this average state sigma bar, that this is included into in L sigma bar, the set of these vectors is the same as the set of inclusion constants for the matrix cube. So the matrix cube inclusion constants also quantify how much you have to shrink this set Q sigma bar around the sigma bar such that it fits into L sigma bar. So that's a different interpretation that also indicates that this set of inclusion constants really quantifies how much steering is in your theory. And here we've just fixed the case, so the number of outcomes to be always 2. So now that we've established what this set of inclusion constants actually means, we want to know what it is, right? So now we want to establish bounds, and we will establish bounds in 2 asymptotic settings, one independent of the dimension and one independent of the number of measurements on Alice's side. And we start with the G-independent bounds. In this case, we can see that the largest S, such that S times the all 1 vector is in the inclusion set of the matrix cube, that the largest such S is this tau d. So it's 4 to the minus n times 2n choose n, where n is d half and then the floor of this. And asymptotically, this behaves as a square root of 2 over pi times d. So that's nice because somehow on the diagonal, we know what's going on for the case which is independent of G. So it only depends on the dimension. And it's actually possible to construct almost optimal steering inequalities in this regime. And the construction is based on epsilon nets of unitary matrices of dimension D. And the whole proof is, which takes a large fraction of our work, is based on the ideas in this work by Helton et al. From 2019, because they study also the matrix cube problem, but for symmetric, so real symmetric matrices. So let's now come to the D-independent bounds. And there we have the following proposition. So if D is large enough, so the dimension is larger equal than 2 to the G minus 1 over 2, where you take the ceiling function, then we can actually know what the set of steering constants is, because it's the same as the positive part of the Euclidean ball, so where all the SI squared and then summed are smaller or equal than 1. And generally for any D, so not only large D, it's true that the set of steering constants contains this this positive part of the Euclidean ball, so which we call the quarter circle. And this also shows that the unbiased steering inequalities considered in this work by Marciniak et al. In 2015 are optimal, because there they consider for d equals to 2 steering inequalities, which are based on Pauli matrices, and in higher dimensions, steering inequalities, which are based on self-adjoint unitaries, anti-commuting unitaries, which are constructed by taking basically tensor powers of Pauli matrices. And with this construction, they find that the violation is lower bounded by square root of G, and we can show that this violation is optimal, which is very nice. So now what implications does this fact that now we know about the set of inclusion constants for the matrix cube have for a quantum steering problem? So let's summarize this in a phase diagram. So remember, what we're interested in is the set of steering constants, so the set of vectors S, such that for any dichotomic steering inequalities, you want to know that if this S has to have this property that if the LHS value is smaller or equal than 1, then the quantum value of the noisy steering inequality is at most 1, because this tells you about the amount of steering in this theory. And the situation looks like this. So there's 3 regimes. In the green regime, where the dimension is large compared to G, we actually know what the set of steering constants is because it's this quarter circle, which is just the positive part of the Euclidean ball. There's the red part, where the number of G is large compared to the dimension. In this case, we know that this tau that we have computed for the G independent regime, that this is outside this set QC here. So in this case, we know that the sigma contains the quarter circle because it always does, but we know it has to be strictly larger because we know that there's at least one point which is outside this quarter circle. So here we know that we haven't established the full truth. And there's this yellow phase here where we only know that sigma is contained, that the quarter circle is contained in sigma, but we don't know if it's equal or not. So if we look at this a bit closer for G equals to 2 and G equals to 3, and dimension 2, because it's the only interesting one, we actually know that we always know what this set sigma is. So this is somewhat settled. But for, say, a G equals to 4 and qubits, so D equals to 2, we don't know that because the brown curve here is outside the red. So we only know that the sigma contains the quarter circle, but we don't know if it's equal or not. It's like the first interesting case. Right. So let me conclude. What have we seen? Well, we have seen that there's a connection between quantum steering and the inclusion of the matrix cube, so like an inclusion of free spectrahedra. This allows us to place an upper bound on the violation of dichotomic steering inequalities for a fixed dimension D and for a fixed number of measurements on Alice's side G. We have shown by this that previously found violations in this work by Marciniak et al. Are optimal. And in particular, we have shown that in the G independent setting, if you consider unbiased steering inequalities, the ratio between the quantum value and the LHS value is at most 4 to the n divided by 2n choose n. And this can be used as a dimension witness because if you measure this ratio here and you find that it's larger than the right-hand side, then you can be sure that the dimension of the quantum system you're considering is larger than the dimension corresponding to this n here, which was defined as floor of d over half. Right. So let me concluding by showing you the references that we have used and that appeared in this talk. And it remains me to thank you for watching this video and watching this talk. If you have any questions, I would be happy if you get in touch. And yeah, here if you have any questions or opinions or you want to discuss. Thank you very much.